We now encounter Michael Faraday for the first time. Faraday made many significant contributions to electromagnetics. This is a daguerreotype of Michael Faraday taken in 1844. Faraday was born in 1791 in a very class-based British society. He was from a lower class, so he didn't get much formal education. His formal education went through simple reading and writing and mathematics. So Michael Faraday had to find a profession. So he became an apprentice for a bookbinder. So as he was learning to bind books, he also read the books he was binding. He was especially interested in the books he was binding that focused on scientific topics such as chemistry. In the bookshop, he was allowed to use a little space where he would acquire some materials and perform the experiments that he was reading about. A patron of the bookbinder gave Michael Faraday a ticket to go to see a lecture by Humphry Davy. Davy was a famous chemist and the director of the Royal Institution. Faraday took detailed notes during the lecture, and he was able to acquire tickets for future Davy lectures, and again he would take detailed notes. He then bound them up very nicely and sent them to Humphry Davy. The bound notes that Faraday sent to Davy must have impressed Davy. Davy, being a chemist, had an accident in the lab and injured his eyes. And so while he was healing, he needed someone who could see and take notes for him. And he thought of Faraday. So he offered Faraday a position as his secretary, and Faraday took it. Eventually, Faraday got involved as an assistant in the lab with Davy, and he was soon designing and performing his own experiments. After Davy retired, Faraday was appointed director of the Royal Institution. Davy made many significant scientific discoveries. He discovered the elements potassium, sodium, barium, calcium, magnesium, and strontium. But as we'll see in this course, his greatest discovery was Michael Faraday. Let's look at one of the experiments that led Faraday to the concept of electric flux. Faraday constructed a series of nested spheres for this experiment. Faraday took a small sphere and put a known charge on it. So let's say he put 8 coulombs on it. He then took an uncharged larger sphere and carefully, so as not to add or subtract any charge from it, clamped it around the smaller sphere containing the 8 coulombs. Next, he attached a ground to this outer sphere. Then he removed the ground. He then carefully removed the outer sphere so that he would not disturb any charge that might be on it, and measured the charge on that outer sphere. What charge did Faraday measure on this spherical shell? You should stop the video at this point and think about it and see if you can figure out what charge he measured. The charge that he measured on that outer sphere was minus 8 coulombs. Let's look at how Faraday explained his results. Faraday said that emanating from the charge on the inner sphere was displacement flux. So if you have 8 coulombs of charge on the inner sphere, there's 8 coulombs of displacement flux emanating from that sphere. Today we refer to displacement flux as electric flux. At this point, there's essentially no difference between electric flux and electric field intensity. We'll later see the difference comes about when we're looking at dielectric materials. So when Faraday clamped the conducting shell around this inner sphere, the positive charge on this inner sphere would attract electrons in that outer shell. Those electrons would stop at the inner surface of this shell. With +8 coulombs on the inner sphere, the inner surface of the shell will have a total charge on it of -8 coulombs. So the electric flux lines would emanate from the positive charge on the inner sphere and terminate on the negative charge on the inner surface of the outer shell. Now this outer shell is neutral, so since you have -8 coulombs on the inner surface, you have to have +8 coulombs somewhere else. And where those +8 coulombs will reside is on the outer surface of that shell. Let's zoom into this region right here. The pluses represent the atomic core, the nucleus, and the non-conducting electrons. The negatives are the conducting electrons. The right-hand side is the inner surface of the conducting shell. The left-hand side is the outer surface of the conducting shell. The sphere charged with the +8 coulombs is to the right, off the screen. So the conduction electrons will be pulled towards the positive charged sphere to the right. And you see what happens is that the right-hand side will become negatively charged and the left-hand side will become positively charged. And the inside of the conductor will remain neutral because the electrons have all shifted to the right. So here's an extreme where the electrons have shifted one atomic nuclei over, so you have a negative charge on the inner wall and a positive charge on the outer wall, and the inside is neutral. The actual amount of charge that shifts is going to depend on the charge on that sphere on the inside. Since in this example we have +8 coulombs on that sphere on the inside, the inner wall here will accumulate -8 coulombs and the outer wall here +8 coulombs. So the electric flux lines start on positive charge and they end on negative charge. Start on positive charge on the outer wall and head out to infinity looking for a negative charge. Right now these electric flux lines are just like our electric field intensity lines. There are no electric flux lines inside the conductor because if there were, you would have current flow. There was a brief current flow to make the inner wall negatively charged and the outer wall positively charged. The charges on the outer wall are repelling each other, and so they become uniformly distributed because that's how they can be the farthest apart. Now Faraday attached a ground to the outer wall of the conducting shell. Let's think about what happens as you bring the ground towards the conducting shell. A ground is an infinite source of negative or positive charges. As the ground comes towards our sphere, the positive charges on the sphere are going to attract electrons. But those electrons are going to attract the positive charges. So they'll start migrating around towards where the ground is approaching. Here we are showing the electric flux lines coming from the positive charge on the outer wall of our shell and terminating on our ground. The flux lines emanating from these positive charges don't have to go out to infinity looking for negative charges to terminate on. They can terminate on the negative charges that are flowing up from the ground. The positive charges are still repelling each other, but now there's an attraction of the positive charges to the negative charges on the ground, and that is why they're migrating around. As the ground gets closer, all of the charges converge. And when the ground touches, these electrons will flow onto the conducting shell and neutralize the positive charges in this vicinity. And now Faraday removed the ground. And so you still had the 8 coulombs on the inner sphere, and you had a negative 8 coulombs on the inner wall of the conducting shell, and no charge on the outer wall. So when Faraday removed this outer shell and measured the charge on it, he found it had -8 coulombs. So he referred to this flux as displacement flux because the 8 coulombs of displacement flux displaced 8 coulombs off his shell, leaving it charged with -8 coulombs. Let's put a charge of Q coulombs on a sphere. From those charges will emanate Q coulombs of electric flux, and the pattern will have spherical symmetry because the charge will be uniformly distributed on the surface of our sphere. Envision a spherical surface in space surrounding our charged sphere of radius r. Since all the electric flux that is emanating from our charge goes through this spherical surface, we know there's Q coulombs of electric flux that will go through it. So we have Q coulombs of electric flux going through this spherical region, and the surface area of this sphere is 4 pi r squared, where r is the radius of our sphere. So the density of the electric flux on the surface of this sphere is Q over 4 pi r squared. We use D as the symbol for this electric flux density. The use of D is probably a remnant from when Faraday referred to this as displacement flux. We know electric flux has a direction associated with it, and for a positive charge on our sphere here, that direction will be in the positive radial direction. So here is the equation for the electric flux density field outside of our charged sphere. If the radius of our conducting sphere is A, the electric flux density field is 0 for r less than A, and for r greater than A, it's Q over 4 pi r squared in the radial direction. If the actual charge is negative, then that would introduce a negative sign, and the electric flux density would point in the negative radial direction towards our conducting sphere, which would have negative charges on it. If we let A shrink to 0, we would have a point charge, and we'd have the electric flux density field due to a point charge. So here is our equation for the electric flux density field due to a point charge at the origin. Recall the equation for the electric field intensity due to a point charge at the origin. We see the only difference between them is this epsilon sub 0. So the electric flux density field is equal to the permittivity of free space times the electric field intensity. As I keep emphasizing, the electric field intensity for point charge is another way of stating Coulomb's law. By writing the constant in Coulomb's law as 1 over 4 pi epsilon sub 0 instead of as a k, we eliminate a 4 pi from occurring in the relationship between the electric flux density field and the electric field intensity. For instance, let's write Coulomb's law with k as our proportionality constant. Then by defining our electric field intensity by dividing by Q sub t on both sides of our Coulomb's law, we get the electric field intensity would be k q over r squared. So to get our electric flux density field from our electric field intensity, we need to multiply the electric field intensity by 1 over 4 pi k. If we have a sphere with Q coulombs of charge on it, we know that emanating from that sphere are Q coulombs of electric flux. Earlier we envisioned a spherical surface that completely surrounds our charge. Through the surface of this sphere, we'll have to pass Q coulombs of electric flux. This electric flux will go through any surface that completely encloses the charged sphere. So if instead we enclosed our charge with a rectangular box, there would be q coulombs of electric flux going through this rectangular box. Let's visualize the following charges. Every minus sign represents minus 1 coulomb, and every plus is a plus 1 coulomb of charge. We know that electric flux lines begin on positive charges and terminate on negative charges. So at least 4 of these lines of electric flux representing 1 coulomb each will go between some of these positive and negative charges. Since there aren't enough negative charges to account for all the positive charges, some electric flux will emanate away. So each one of these lines represents 1 coulomb of electric flux. So this dashed line represents a closed surface that completely encloses these 4 negative 1 coulomb charges. So the charge enclosed by this surface is minus 4 coulombs. And we also have 4 coulombs of electric flux entering this closed surface. Now let's form a closed surface that encloses these 3 plus 1 coulomb charges. Now we have 3 coulombs of charge enclosed by this closed surface, and there are 3 coulombs of electric flux leaving this closed surface. Now let's pick this closed surface. So now we have minus 1 coulomb enclosed by this closed surface. We have 1 coulomb of flux leaving and 2 coulombs of flux entering. So we have a net of 1 coulomb of electric flux entering our closed surface. So the charge enclosed by a closed surface is equal to the electric flux leaving that closed surface. So if you have 3 coulombs inside the closed surface, there's 3 coulombs of electric flux leaving it. If you instead have a negative charge enclosed, like minus 3 coulombs, then you would have 3 coulombs of electric flux entering your closed surface. The mathematical description of this is called Gauss's law, and that will be the topic of another video.